All right, today we're going to take a look at the third lesson in probability. And we're going to talk about the multiplication rules and then using Venn diagrams. First thing we want to talk about is what the multiplication rule and its properties are. So we'll read through this, and it says, and notice how it's written, probability of A and E is the probability that the event A occurs in the first trial and B occurs in the second trial. To find the probability of A and B, we must use multiplication. And what this is the probability of A and B. We find that by multiplying the probability of getting A times the probability of getting B, given that A has already happened. And we're going to need to know a couple of terms as we go through this, and these are kind of self-explanatory definitions. One of which, two events are independent if they occur on one, if the occurrence of one event does not affect the probability of the occurrence of the other, and vice versa. So they are not going to affect one another, they are independent. If one event affects the probability of the other, it is known as dependent. When two events are independent, the probability of selecting B, given that A has occurred, will always be equal to the probability of just getting B. And that makes sense if you stop and think about it. You may not be familiar with our phrasing here, but if A has no bearing on B, then A cannot affect the probability of selecting B. Let's take a look at a couple examples here and see what we've got. First of all, two cards are drawn from a standard deck without replacing them. What that means is if I select the card, I'm going to sit it to the side. I'm not going to put it back into the deck. So whereas I have 52 cards on a first draw, when I set the one card to the side on my second draw, it would be 51. So the events that happened in the first draw have affected the events of the second draw. So this is one of those dependent events. The event 2 happening is affected by the event 1. So what we have here is, what is the probability that you draw two kings in a row? Well, the probability of selecting the first king is 4 out of the 52 cards are kings. So that's our probability of selecting A. And then probability of selecting B. Well, now that I've drawn that king, there are only 3 kings. And since I've drawn that king and set it to the side, there is only 51 cards as opposed to 52. So the way we get the probability of these two events is we multiply the probability of each together. So when I put this into my calculator, what I get is 0.0045, and it continues on. And I'm going to hit math, enter, enter. When I do that, I learn that the probability of this happening is 1 over 221. It would have ended up being 12 over 2,652, but we can go ahead and let our calculator reduce this fraction for us. So that is the probability of that two kings in a row being selected. Again, we are still working without replacing. So what is the probability of selecting two diamonds? Well, there are 13 out of 52 diamonds, but we're going to go ahead and reduce this fraction. 1 out of 4 are diamonds. Now on our second draw, we have eliminated one of the 12 diamonds, and when we do these probabilities, we treat it as if the event has happened in order to calculate probability. Even if it's an improbable chance, we still treat it as if it happened. So the probability of selecting a second diamond, well, now there are 12 diamonds, out of 51 cards. So we multiply this together and we get 12 over 204. Both of those are even numbers, so we know this is going to reduce. And it reduces to a 1 in 17 probability. All right, let's move to probability of C. Our probability of selecting a king, well, that is 4 out of 52. It's 1 out of 13, but we'll just stick to this. Now, the probability of selecting an ace. Well, there are now 4 aces still left in the deck, but we are drawing from 51 cards. So we have 4 times 4, 16 out of 2,652 as our denominator. So our probability is 4 out of 663. Now I'm going to put the percentage chance, because that number, I can understand the other two, but that one's a little tougher to understand. What the number is 0.00603. So we move our decimal place over twice, and what we have is a less than 1% chance of this happening. A 0.6 chance of happening, actually. So there we have it. Now we're going to do the same exact thing, but we are going to replace the card in the deck. So what we've done is we've taken the experiment and changed it from a independent situation, and now we are going to deal with a dependent. So the probability of drawing 2 kings in a row, well, 4 out of 52 are kings. So when I draw the first king, since I put it back in the deck, I still have 4 kings that I could draw from. And since the king was returned, I also have 52 cards to draw from. So we have 4 over 52 times 4 over 52. Really, we have 4 over 52 squared. If you think about it, you could put it in your calculator this way, and we have a 1 over 169 chance of this happening. So compared to our original, when we did not replace 221 as a denominator. Now the probability of selecting 2 diamonds, well, 1 out of 4 diamonds on the first draw. And since we put the card back in the deck, we still have a 1 in 4 chance. 1 times 1 is 1, 4 times 4 is 16. So we have a 1 in 16th chance, again, better than our 1 in 17 chance. And then the last one, I am going to reduce this one. 1 out of 13 cards in the deck is an ace, king, and 1 out of 13 cards in the deck is an ace. It did not affect the chances there, so we leave our denominator the same. So the chance of this being selected is 1 out of 169. Exactly the same as selecting 2 kings. Let's take a look at this next example. Consider a quiz that has 2 questions. First is a true-false, and the second is a multiple choice. Options A through D. What is the probability of getting both answers correct if you randomly guess? Now that's an important thing when we talk about statistics. We are dealing with random events. Now hopefully if you're taking a quiz, they're not random events, so This is not your chances of getting 100 on the test. This is your chance of getting a 100 if you are random guessing. So in our first question, we have a 1 out of 2 chance of getting it correct. It's true, false. It's either true or it's false. It's either right or it's wrong. One choice is good out of 2. Now, the second question is a multiple choice question. Whatever the answer is, A, B, C, or D, there is only one way to get it correct. Since we have A, B, C, and D as an answer, our sample size is 1 out of 4. So the probability of guessing this both correctly randomly would be 1 in 8 chance. And this is an example of an independent event as well, because neither would ever affect the other. All right, consider a bag of 15 green marbles. 15 green, 20 black, and 25 red. If you draw 4 marbles, so we're going to have 4 slots here. First choice, second, third, and fourth. If we draw 4 marbles, replacing the marbles each time. So these are independent events. What is the probability of first drawing a red marble, then another red, then a green, then a black? Well, the first thing we need to do is figure out how many marbles we have. We have 60 marbles in this bag. So the probability of selecting a red marble is 25 out of 60. And we are replacing the marbles. So I could draw that one that I just drew again. So there are still 25 red marbles in the bag, and there are still 60 total marbles in the bag. So that would be our first probability, 25 out of 60. And the third one was a green marble, excuse me. There were only 15 green marbles out of the 60. And then it finally says the probability of selecting a black marble. Well, there are 20 black marbles out of 60. If you want to reduce as you do these, you're welcome to do that. On the other two, I couldn't do it quite as easily, but I know that 20 over 60 is 1/3. So when I go to take that and put it in my calculator, I'm going to go ahead and reduce that so it's easier to calculate. So my probability is reduced 25 over 1728. Now what I'm going to do is I'm going to convert this into a decimal so I can recognize what my percentage is, because I don't really understand that number. So this number is approximately 0.01446. So as we look at this, this is when I move the decimal place over 1 2 times. It's essentially 1.45%. All right, as we look at this example, if you were paying attention in the notes, you would recognize that this is really one of the formulas we have. But we are just going to basically prove this formula. So let's take a look at this and see. So here's what we have. The probability of E is 0.4. And the probability of E and F is 0.21. So the way that we find the probability of F is, remember, we get this by multiplying the two numbers together. Probability of E times the probability of F equals the probability of E and F. So we set our formula up to multiply the two. This is probability of E. This is the probability of F. So all we have to do here is divide both sides by 0.4, and we will have our probability of F. So we divide by 0.4, and we learn that the probability, it is actually equal 0.525. So that is our probability of selecting F given that E has occurred. So we're going to start with a very simple Venn diagram on this. It says, draw a Venn diagram for the scenario and then answer the question. It says 22 students, children are playing on a playground. 10 are wearing shorts, 12 are wearing pants. One is chosen at random. Well, these two events are independent of one another because you can't wear shorts and pants at the same time. So when we set up a Venn diagram, we look at this way. Now, a couple of things about a Venn diagram, and I didn't intentionally do this, but this does come to mind. The size of the circles don't matter. All they're doing is basically laying out a boundary. And matter of fact, in this one, you can see my shorts circle is larger than my pants circle, even though shorts 10 and pants 12 are not proportionately set up this way. So let's go ahead and solve our proportions here. We'll try to keep our Venn diagrams in the picture. Maybe not. There we go. So the probability of choosing a kid with pants, well, 12 of our 22 are wearing pants. So our probability is 6 out of 11. We'll leave them in fraction form for this section. Well, here's the thing about only having two options. We could sit here and create a formula, but if 6 out of 11 are wearing pants, that means the remaining 5 are not. We're wearing shorts, excuse me. Hopefully they're wearing some kind of pants. And we could have set this up as saying 10 out of 22, but we know that that is the converse, so we could do this. All right, what is the probability of selecting shorts or pants? Well, 10 are wearing shorts, 10 out of 12, plus the 10 out of 22, excuse me, plus the 12 out of 22 that are wearing pants. So that is a 22 out of 22. So the probability is 1. You're going to select a student that is wearing pants or shorts, excuse me. Now, pants and shorts are mutually exclusive events. So our probability of selecting one that is wearing both is 0 out of 22. So the probability is 0. All right, let's take a look at our next Venn diagram. So as we take a look at our Venn diagram here, it says we have a class of 19. 18 have brothers. So we have a brother aisle, a box, excuse me. And then it says there are 14 that have sisters and 13 that have both. So we do have some overlap in this one. And again, do not let the size of the portions dictate anything, because if you notice, 13 have both. So we learned that they had 18 that had brothers. That would be in this circle we first drew. 18 are in this circle, big circle. So if 18 are in the double, that leaves us with 5 that just have brothers. 5 that just have brothers. Now, of the ones that have sisters, The circle right here consisted of 14. And 13 are in the overlap, which means there is only one person that only has a sister. And then the last part said there were no only children. What you want to do is add up all your circles, make sure they equal the number that it's supposed to. 5 and 13 do make 18, plus 1 does make 19. All right, probability of a brother or a sister. Well, it told us that there were no only children. So if you have a brother or a sister, that is all 19 of 19 students, a probability of 1. Our probability of selecting someone that has a brother. Well, that is the 5 that only have brothers and the 13 that have both. So the probability of having a brother is 18 of the 19 students. And these two are converse thoughts too, because contrary to brother is not having a brother. But we can still look at our Venn diagram. This circle right here represents the brothers, so the only ones that did not fall in that is the one student out of the 19 that only has a sister. So this is how we create probability with multiplication. Again, when the events affect each other, you have to affect your multiplication. But each time we add a new event, we multiply the probability of the first times the probability of the second times the probability of the third. Now we're going to get ridiculously small numbers, but you treat it as if it's going to happen. Regardless of how unlikely it is, you treat it as if the previous event did happen. That's how we calculate probability. All right, you have a CAMI assignment on this one. Good luck.